So yesterday, last class, you guys walked out of here. You had homework out of a packet, page 271. So problems 1 through 10 there, you were actually 1 through 13 you were assigned. Any questions on those you want me to go over? Which one? 10. Number 10? Okay. 230 volts, 0.75 horsepower. Motor has an efficiency of 0.76. Determine the motor's output power in kilowatts. Well, the 0.75 horsepower is its output. So you take 0.75 horsepower and you have to convert that into kilowatts. So we're going to make a fraction here. We're going to put horsepower on bottom. We're going to put watts on top, which is 746 watts to 1 horsepower. Come on. There we go. Horsepower cancels out. 0.75 times 746 is 559.5 watts. Now, but it says in kilowatts, so that's going to be 0.5, we're going to say 0.56 kilowatts. We'll round it to. Just moving the decimal place 3 spots. Make sense so far? Even to Jordan? Okay. Part B, the current. Well, remember, power is current times voltage. If we have 559.5 watts, notice I went back to the wattage, not the kilowatts, equals my current, come on now, got 230 volts, so it's going to be current times 230 volts. So we will solve that by dividing by 230. So 559.5 divided by 230 is 2.43 amps. Come on now. So that's our current, 2.43 amps. Actually, you know what? You know what I screwed up there, though? We've got to consider the efficiency here. Is that what you got for amps, is the 2.43?
No, you know what I did? I did the horsepower as the.
Gotcha. So what we have to do here is we have to consider the efficiency here of the 0.76. And since we have an output of that 0.75 horsepower, 559.5 watts, we have to take that 559.5 watts divided by 0.76. Actually, set it up for you guys. Remember, it's P out over P in. So the 559.5 watts is the P out, the output. We're looking for the input power, and it's a 0.76 over 1 is the efficiency. So we'll cross multiply and divide. Gives us that input power. So we are dividing by 0.76. Gives us 736.18. That is watts. So now we're going to take that to find our current. So it's times 230 volts. So we're going to divide by the 230. to get 3.2 amps is our current. Now the cost of operating for 2 weeks at 10 cents per kilowatt hour if it is operated for 6 hours per day. Well, first of all, 736.8, we're going to make that 0.74 kilowatts is its power consumed. Times 6 hours per day times 14 days. So this is going to be the 0.74 times 6 times 14. Gives us 62.16. That's kilowatt hours. Then we multiply that times our 10 cents. So that's $6.22, $6.22 cost for 2 weeks. So, we talked about ratios for efficiency and stuff like that last week. This week we want to talk about some things. The first one here is actually a little bit of a review. We've talked about part of this, that the resistance in a wire is related to the length of the wire. If the resistance gets longer, if the length of the wire gets longer, does the resistance get higher or lower? Does a longer wire have more or less resistance? Total resistance. More resistance. Very good. More wire to go through, more resistance. That's what's called a direct relationship. So if I have 480 feet of wire that has a resistance of 16 ohms, what will be the resistance of a 60-foot piece of that wire? Well, the resistance, R1 to R2, is proportional to the lengths. Length 1 to L2. So we have the 16 ohm resistance, which goes with the 480 feet. Our new resistance will go with the 60 feet. So we'll solve by cross multiplying and dividing, and what do we get? Two ohms? Thank you. So that one is relatively straightforward. And we've seen that one before when we were first starting to talk about ratios and stuff like that. But the one that's a little less obvious is the relationship between resistance and diameter of wire. Which wire would the electricity flow through more easily? Little one or a big one? This one sounds like a trick question, but it really is the big one, yeah. If you think about like water through a pipe, a bigger pipe, the water can flow through a lot more easily, a lot faster than the little pipe. You get the same water through the little pipe, it's got to move way faster. And also it's the ratio of area to side is different. So you got more, they call it viscous friction. Anyway, the bigger the diameter, if the diameter goes up, the resistance goes down. This is what's called an inverse relationship. So in an inverse relationship, one of two things has to happen. Either we have to change the way we set it up, and often resistance 1 times area 1 has to equal resistance 2 times area 2. The resistance times the area is a constant for the type of conductor, as long as the length of the wire is the same. So this is requiring that we have the same length of wire. So the total amount of resistance will decrease with the area. So let's say that this wire here has a diameter of 0.08 inches. And this wire here has a diameter of 0.20 inches. And our smaller wire is cut to a length that has a resistance of, well, let's go with, let's just make it simple. Let's go 25 ohms. So we want to know the resistance over here. So we would have, first of all, we'd have to find the area here. The area of this one is going to be pi times what squared? 0.04. That's the diameter, we need a radius. Over here, it would be pi times 0.1 squared. And give us the areas. Come on now. So 3.14 we've been using for pi. That gives us 0.005024. That'll be square inches for the cross-sectional area of the first one. Over here, this will be 0.0314 inches squared for the cross-sectional area of the bigger one. So we would set this up, R1, 25 ohms, times 0.005024 has to equal R2 times 0.0314. So to solve that, we multiply the 25 times the 0.005024 and divide by the 0.0314. We get 4 ohms for this. Does that make sense? Well, that's kind of a pain in the butt to have to do this area calculation. So let's look at how we can maybe work with that a little bit easier. There's an alternative formula for area. The alternative formula is the area is pi times diameter squared divided by 4. Where that came from, of course, is the radius is the diameter divided by 2. And when you square the radius, we get diameter squared and the 2 squared. So it's diameter squared over 4. If we look at that, if we were to put that in this formula here, we'd have R1 times pi times diameter 1 squared over 4 equals R2 times pi times diameter squared, diameter 2 squared over 4. Well, if we look at this, we can divide out the 4s and the pi. I shouldn't say divide out. Cancel out the 4s and the pi's on each side. And what we end up with here is R1 times D1 squared equals R2 times D2 squared. So rather than finding that area, we could have used just the diameter squared. We could have done this as 25 times 0.08 squared equals blank times that was 0.2, right? Yep, 0.2 squared. So all we'd have to do is 25 times 0.08 squared divided by 0.2 squared, and we would get the 4 ohms resistance. A lot simpler. When I have inverse relationships, this is the way I like to set it up. Direct relationships are a constant ratio. They're equal ratios. This is like the length. So we had R1 over R2 is the ratio of L1 over L2. Inverse relationships are equal products. Instead of equal ratios. So that's where we got this formula. R1 times D1 squared has to equal R2 times D2 squared. That's the way I prefer to have them set up. But a lot of textbooks and a lot of manuals like to keep this proportion set up. So it's cross multiply and divide. So what they do is this. They solve this ratio. They divide both sides by R, and then they divide both sides by D2, and they get this. Now, what I don't like about this proportion here is I have preached to you for a couple of weeks now that proportions have to have relationships in both directions. These two are from the same wire, and these two are from the same wire. These two both describe resistance. These two both describe lengths. Well, over here, you see that that doesn't fit. You know, these two are the resistances, and these two are the diameters, but, oops, I did that wrong, didn't I? Give me just a second here. Put the wrong numbers in here. I solved that, right? It should say D2 over D1. I'll give you a second to erase that in your notes. So now that I have that set up correctly there now, you can see it's confusing because this is R1, but D1 is on the bottom. And that's the inverse ratio. And the inverse ratio, they have you invert the second ratio. You flip it upside down. That's why, to me, this idea of a constant product makes more sense. You've got wire 1 both on the left side, you know, the resistance and diameter of wire 1 on the left side, resistance diameter of the wire 2 on the right side. But you are going to see it most commonly in textbooks and manuals set up like that. And like I said, that is an inverse ratio. When instead of having things related straight across like we're used to, it's the diagonal ones that are related. And the reason for that, like I said, is they've taken this second ratio and flipped it over for the inverse ratio. So if you want to take a look at resistances here in wires, there's a chart here I got to get to. Where is it? Page 277 in your packet has a chart of wire gauges and sizes. So let's say that we do not know the length of a wire, but we do know that a piece of 12 gauge wire has a resistance, oh, let's say, oops. Oh, let's give it a resistance of 3.8 ohms. I want to find the resistance of the same length of, let's say we drop that down to a 16 gauge wire. Have you guys been over wire gauges at all? The bigger the gauge, the smaller the wire. Okay. So looking up in this table here, the 12 gauge wire, now I can either use the metric or I can use the English. It really doesn't matter. If we use the English, The 12 gauge is 80.81. That's in mils. A mil is a milli-inch. So 80.81 is actually 0.08081 inches. Does that make sense? Now, fortunately for us, we're not concerned about the exact measurement. We're concerned about the ratio. So we could use it as mils if we wanted to. So let's set this up. We've got R1 over R2 equals D2 squared over D1 squared. We're going to use the standard textbook formula here. We've got R1 of 3.8 ohms. Now, where is the 80.81 mils going to have to go? It comes from the same wire as the 3.8, but this is an inverse relationship. You see, R1 and D1 are diagonal. So 80.81 goes down here, and it is diameter squared. We're looking for this resistance. We're going to a 16 gauge wire. 16 gauge wire has a diameter of 50.82. So we'll put 50.82 squared there. So any questions so far? So now it's just a matter of cross multiply and divide to find that resistance. So 3.8 times 80.81 squared divided by 50.82 squared. 9.61, we'll call it, ohms. So you don't think going from 80 mils down to 50 mils should have that big of an influence, but it triples your resistance pretty much. The other thing they have here is they actually have resistance per foot. Let's say we have, resistance per 1,000 feet. So let's say I have 4,000 feet of wire with resistance of 20.256 ohms. What gauge wire is that? Well, the chart here is ohms per 1,000 feet, correct? So this is a direct ratio. All we're worried about is the length here. The resistance changes for length. So we've got 20.256 ohms in 4,000 feet. We want to know how many ohms that would be in 1,000 feet. If we cross multiply and divide, it comes out to be 5.064 ohms, correct? So looking at that chart on page 577, can you find a wire that is 5.064 ohms, per 1,000 feet? (17 gauge). Any questions on that? Okay. So other things that affect the resistance of our wires, to actually calculate the resistance of the wire, if you know the properties of a wire, let's flip to page 280 in the packet. On the top of page 280, there is something called the resistivity. Resistivity is a property of any metal. Any metal has a measurable resistivity. And what it is actually the ohms. If you know the length of the wire, diameter, all that stuff, it is calculated as the ohms per unit of length of the wire. but it also has to take into account the diameter, area of the wire, and all that good stuff. But you can see silver as a metal has an incredible resistivity of 0.0164 times 10 to the negative 6. It's a very low resistivity. Why don't we use silver for wiring and stuff like that? Pure silver corrodes extremely rapidly. So any connections and stuff would be corroded. It would not work well. Copper, you can see works 0.0172 times 10 to the negative 6. Not a whole lot worse than silver, but copper, the weird thing about copper exposed to air does corrode quickly, but as long as it's making tight contact with other metals, where it's not exposed to direct air, like so when you make connections with it, it doesn't corrode between those connections. And then aluminum. Resistivity of aluminum is 0.0283 times 10 to the negative 6. So you can see aluminum has a lot higher resistivity, which means it has a higher resistance. Now in the 1970s, copper was becoming very expensive. It's actually extremely expensive now. But because of the price of copper, for a short period of time, they actually stopped using copper wire to wire houses, and they started using aluminum wire. Well, there were two problems with that. One is the aluminum wire had a lot more resistance. It was harder for electricity to flow through aluminum. So they actually used larger wires. If you ever look in the walls of a house and you see wires that look like they're bigger than normal, there's a chance those are aluminum wires. The other problem with aluminum wires is aluminum hardens. It actually heat treats it just a little bit above room temperature. So when there's electricity flowing through a wire, what happens to it? It gets warmer, heats up a little bit. Doesn't take much heat in an aluminum wire. Doesn't take much heat above room temperature for that aluminum wire to actually heat treat. Heat treat makes things hard, but it also makes them brittle. So any flex in the wall, it would crack that aluminum wire. And once the aluminum wire cracked, what's going to happen when you push electricity through it? Well, right here, there's going to be a spark, right? As long as that's close enough together, the electricity is going to jump. It's going to spark across. Well, what happens when electricity sparks from one conductor to another? It gets really hot. Well, if it gets really hot, that extremely heat treats these ends, and they start to crumble. And what will happen is the spark has to jump further and further to get across that gap that's created by the crumbling aluminum, and eventually it sparks big enough to light something else on fire. So aluminum wiring was a huge fire hazard. You can see that there is a large enough difference in the resistivity that you can actually measure. You can take a piece of wire, even if you don't know the exact length, you can measure the resistance in that piece of wire with an approximate length, and you can usually tell whether it is copper or aluminum. So the formula here, the resistance of a wire is, excuse this. The resistivity in a wire, uses that symbol rho, is equal to the resistance of a piece of wire times its area divided by its length. Now in this form, this formula isn't very useful. We know the resistivity of the wire. Now what this would be for is, let's say you are actually going to test a piece of wire. You've got a house. Let's resort to my beautiful drawings again. You go down into the basement of a house, you find the electric box. You've got the wires coming, you got wires going out. What I ran into, I used to do a lot of home inspections for people buying houses. And the first thing you do is you go down here and you open up the electric box and you look to see if there's gray wires. I mean, the difference between aluminum and copper visually is very different. You look to see if there's gray wires coming into the box and going into the breakers. If there are gray wires, then there's aluminum wire in the house. Well, because of that, some not so ethical, I don't know if it was homeowners or the electricians they hired, what they would do is they would take that aluminum wire here that goes up through the floor into the house, they would pull it down, they would snip it off, splice copper onto it, shove it back up into the floor, and just run copper into the main box. So you open it up and you saw copper. So what you would do is you would find a spot where you were pretty sure the wire went relatively directly from the box to that spot. So let's say you find an outlet up here. So that outlet, let's say we found the distance here, and we know it's pretty sure it's going to be about 20 feet of distance between there. We have a 12 gauge wire. And let's see, so 12 gauge wire, we got to find this area. We flip back. I should have these memorized, I used to. These are in meters, so we got to have the meter, the centimeter one anyway. So 12 gauge is 2.053. Now this is millimeters. You'll notice on that chart on page 280, it's ohm meters is the unit there. So what happens is in this formula, it works out really nicely. That 10 to the negative 6 on those resistivity constants is going to disappear for us. So what we're going to do is we're actually going to convert each of those into ohm millimeters. And then all we're doing is we're dropping the 10 to the negative 6. So we're going to go ahead and we're going to find what is the cross-sectional area of this. Well, it's going to be pi 3.14 times 2.053 divided by 4. 2.453 squared, I should say, divided by 4. Remember, that's just diameter squared over 4 instead of radius squared. So 3.14 times 2.053 squared divided by 4. So your cross-sectional area there is 3.309. And that is millimeters squared. So in our formula over here, that goes in for our cross-sectional area. Our length is 20. Let's say we hook up the meter and measure the resistance, and we get a resistance of 0.171 ohms. So we'll put that in here. So what we're going to do is we're going to multiply resistance times the area and then divide by the length. Now I have that length in feet. Let's change that. That should be 20 meters. So 20 feet because we are using the metric constants. So that's 20 meters we're going to put that as. So our units stay consistent. So we're measuring our diameter in millimeters. Our length is still in meters. So if we calculate that out, 0.171 times 3.309 divided by 20, we get 0.0283. Looking at our chart, which constant, which material has a constant of 0.0283? That's an aluminum wire. Now I did that example so it came out on the nose, but chances are because there's that little piece of copper, it might come out at 0.0245 or something like that. That's telling you that that's way more resistance than what you'd expect it to be if it were copper all the way. Now there's a little bit of fudge factor there because let's say it came out to be like 0.019 or something like that. Copper's 0.017. that wire might be a little longer than you expect it to be, or there's connections in that wire. So I mean, you gotta have a little bit of fudge factor. But it was actually very common. In fact, there's a house on 48 here over by Cumberland that I inspected that they actually had done this. They had actually clipped off the aluminum wires, spliced copper. So there was copper going into the box and hid the splice into the floors, which is doubly wrong because you got the aluminum wires in the walls, but now you've got a spliced wire shoved into the wall as well, which is really bad. The more useful form of this formula is to rearrange it. Instead of, if you're testing wires like we just did, instead of the resistivity equal R times A over L, for testing wires, this formula is great. You can calculate the resistivity of a current wire, and you can figure out what the metal, what the conductor is in that wire, if you don't know. The other side of it, though, is usually what you want to find is what the resistance is going to be in a certain piece of wire. So let's say we have a 14 gauge copper wire that is, and we're going to keep operating in meters here. Let's say it is going to be 230 meters long. So we need to rearrange this formula and solve it for the resistance. To do that, I'm going to multiply by L and divide by A. So that tells me the resistance is the resistivity times the length divided by the area. So my resistivity of copper, 0.0172. Remember, we're dropping the times 10 to the negative 6 because we're doing our area in square millimeters instead of square meters. Times our length is 230 meters. Divided by our area here is going to be pi, 3.14, times 14 gauge is 1.628 squared over 4. So 0.0172 times 230 divided by, now I got to put this in parentheses here for the area so I get it all in the denominator. 0.314 times 1.628 squared divided by 4, and close my parentheses. I get 1.901 ohms. So 230 meters of that wire should be about 1.901 ohms. Let's double check that. That chart gives us a resistance per kilometer, per 1,000 meters. So on 14 gauge, it says 8.285 ohms per 1,000 meters. What would that be for 230 meters? So 8.285 times 230 divided by 1,000. And we get the same result, 1.906 about. Close enough. Make sense? Yeah. For this formula, everything is supposed to be in meters. But the only reason we went with millimeters is because that constant is, 0. Where the heck is it now? 0.172 times 10 to the negative 6. Exactly. So millimeters instead of meters, because you're squaring that diameter, that takes it 1,000 times 1,000. So that's a million, which is 10 to the 6th, which cancels out that 10 to the negative 6. So that's why we're able to ignore that 10 to the negative 6 on there. Because instead of putting our diameter in meters, we're doing it in millimeters. And so they divide out. I would personally prefer that they redid this table. I just cannot find a table that's done in ohm millimeters so that it comes out. So we just have to use the table and ignore the 10 to the negative 6. The other thing with resistance, one last thing and we're done, I promise. I only got 6 minutes anyway. Is temperature. If it gets colder, what happens to resistance? Do you know? Resistance goes down. As the wire gets hotter, the resistance increases. Most people think if it gets hotter, it moves easier. It doesn't. When a wire gets hot, the resistance increases. Hot wire is more resistance. The constant is 234.5 degrees. That is negative 234.5 degrees. At that temperature, copper has zero resistance. Have you ever heard the term superconductors? All conductors are superconductors at the right temperature. If you can get copper down to negative 234.5 degrees, it has zero resistance. It's a superconductor. Well, the whole art behind superconductors is to create materials that don't have to be nearly that cold to have zero resistance. I think the warmest superconductor was like negative 150 degrees. If you guys are curious, you can look it up. It changes every year as they're doing research. But copper has zero resistance at negative 234.5 degrees. So, and that is, it's called degrees, it is in degrees Fahrenheit. So we're using, it's degrees Celsius, I should say. So it is in our Celsius system. So if I have a wire that has, let's say it has 3.8 ohms of resistance at 20 degrees Celsius. 20 degrees Celsius is roughly 68 degrees Fahrenheit. What will the resistance be if the temperature goes up to 30 degrees Celsius? 30 degrees Celsius is like 86 degrees Fahrenheit. So it's an 18-degree jump in temperature. What we have to do over here is we have to consider this is our base temperature, negative 234.5. So what we do is it's 234.5 plus the first temperature, and 234.5 plus the second temperature. We're adding that 234.5 to each temperature to get it down to that base. So for the first one, 3.8 ohms over, we're trying to find that resistance. It's going to be 234.5 plus 20. Down here is 234.5 plus 30. So this is 254.5. This is 264.5. So you can see not going to be a huge difference. Cross multiply and divide here. Come on. 264.5 times 3.8 divided by 254.5. We get 3.95. So that increase of 10 degrees Celsius causes a 0.15 ohm increase in resistance. Okay. You guys have suffered enough for the day, so let's give you some homework. Out of this packet, yes, this is a lot of pages. No, it's not a lot of problems. Page 275, 1 through 6. Page 279, 1 through 6. Page 281, 1 through 6. And page 283, 1 through 4. Again, just different ways of adjusting resistance for temperature, length, material, all that good stuff. Okay, you only got a minute left, so I won't make you stick around and work for that. See you guys.